In this lesson, we'll talk about contradiction proofs. The idea of a contradiction proof is that sometimes when you're doing a proof directly, you just run into a snag very easily. If for some reason or other it's just difficult to use the assumptions, or maybe just the proof itself, the statement is a really strange thing to prove. Sometimes it helps to be able to prove indirectly. This is the first of those methods called the contradiction proof method. In order to prove by contradiction, what we do is we'll assume the negation of the statement. Now for the negation, it's usually pretty easy to spot, but we'll do that example by example. After we assume the negation, we will show that this gives us something completely false, which we call a contradiction. What do I mean by completely false? Here's a few examples of things that could be a contradiction in the proof itself. First off, you could find some statement P, so that when you have P happening, then negation of P happens at the same time. You know that P and its negation cannot both be true, so that would be an example of a contradiction. Another one is that you'll assume something has a smallest property, or perhaps a largest property, and then perhaps find something else that's even smaller or even larger. One other contradiction is to show that an empty set has an element. We know that empty sets are empty, so if you end up showing that it has an element, that's a contradiction as well. Here's some good times to use contradiction. One of the number one ways is to try to show that something does not exist. It's pretty hard to show it doesn't exist, so using the opposite sometimes helps. To show that a set is empty, sometimes it's useful to assume it has an element and show that that brings a contradiction. And then finally, to show that a set is infinite. It's kind of hard to show something's infinite, so it does help sometimes to assume it's finite and then find a contradiction to that. Here's our first example. Let's show that the positive reals does not have a smallest element. What we're going to be doing is we're going to do a proof by contradiction. What this means is we'll assume the opposite. The opposite of this statement is that the positive reals does have a smallest element. If it does have a smallest element, let's call it out. Let x be the smallest element of R+. This is where we ask the question that we usually do. What does that mean? Well, if it's an element of R+, that means it's a real number, of course. And it also means that it is positive. Then x is an element of the reals, and x is greater than 0. Now, the idea is that x was the smallest element. If we want to find a contradiction, we're going to need to find an element of the positive reals that is even smaller. So you might ask yourself the question, what are some ways that you can shrink a number? That you can make a real number smaller than it was already? One idea you may have is subtraction. But if you subtract anything, that might take you out of the positive numbers. Another one, and this one does work, is you can divide by something like 2. And I believe everyone can agree with me there. If you take a positive number and you divide by 2, you get a positive number. Let's explain that just a little bit. Since 1/2 is less than 1, we get x over 2 is less than x by multiplying by x. Our value is going to be x over 2. We just showed that it was smaller than x, so as long as this is in the positive reals, we're good. Also, x over 2 is greater than 0 since x is greater than 0. That does it. Then x over 2 is an element of the positive reals and is smaller than x. That's our contradiction. We just found an element that was smaller than the smallest element and is an element of the same set. So we have just contradicted the fact that x was the smallest element. Usually we mark a contradiction with this symbol. There are many different symbols that you can use for contradictions, but this is the one that I learned when I was taking this very same course. You might use a different one in your class, or come up with one that's completely different entirely. Now that we have our contradiction, we can write our conclusion. Thus, the positive reals does not have a smallest element. Here's your next statement. A intersect A complement is empty for all sets A. Now I think that's pretty believable. What it boils down to is to be in a set and to be in its complement really would mean that you're inside the set and outside the set at the same time. That doesn't really make sense to talk about. Let's prove this by contradiction. First off, we're trying to show this for all sets, So let's pick our arbitrary set. Let A be a set. Now, if it's going to not be empty, what that means is that there is an element of the set. And assume X is an element of A intersect A complement. The usual question here is, what does that mean? Then X is an element of A, and X is an element of A complement. But again, what does it mean to be an element of A complement? So, X is not an element of A. But this is a contradiction right here. We have that X is an element of A, and X is not an element of A. That's a contradiction. So now we're done. Thus, A intersect A complement is the empty set. Here's our last statement for this video. The set of integers is infinite. Let's prove this by contradiction. The negation of this statement is pretty obvious. It would say that the set of integers is finite. What does that mean? For a set to be finite, that means that it has some cardinality. Let's do that. Suppose the cardinality of the set of integers equals n for some n in the natural numbers. Now somehow I have to prove a contradiction to this. What I'm going to do is actually show that n is not enough to contain all of the integers. Consider the set S equals 0, 1, 2, and so on, all the way to n. I believe everyone would agree that every single one of those numbers in that set is an integer. Here's what we have. Then S is a subset of Z, and the cardinality of S equals n plus 1. We actually have a contradiction already. Recall that if you have a subset, the cardinality of the subset will always be less than or equal to the cardinality of the other set. But n plus 1 is not less than or equal to n. Thus, n plus 1 is less than or equal to n, and that is definitely a contradiction. There we have it. We have a contradiction, which means that there is no cardinality you can associate with the integers. Hence, Z is infinite. And that is the end of our proof. Let's talk about the new styles of proof here. How do you prove a statement P by contradiction? What do you think? Assume that the negation of P is true, then show that this leads to a contradiction.